And we take you to the practice quiz. So go ahead and do A and B. And 30 more seconds. Okay, so fractional exponents was not really the focus last time, but it's related because it's exponents. And the top number is trying to make 4 to the third. It's trying to make it grow. The bottom number is doing the opposite of that. If it was also a 3, they would neutralize each other out and it would stay at 4. It would be cube rooting in that case. Right now, it's square rooting. So the bottom number comes out here. The top number, now I can put the 3 here or I can delay it. I like to delay it because then I'm working with smaller numbers. 4 cubed, I need a calculator, and then to take square root of that, I might need my calculator, and this I can do in my head. 2 cubed is 8. Now notice, the 3 was bigger than the 2, so it won in the war of exponents. It made the 4 larger, go up to 8. If it had been the bottom number bigger than the top number, it would have shrunk the 4 to a smaller number than 4. All right, negative exponents. If we think of an exponent as repeated multiplication, a negative exponent might be thought of as repeated division. It's like dividing by 2 3 times. Dividing by 2 is the same as multiplying by 1/2. Alright, give me a little feedback on these two with numbers. And I start with numbers because we're going to get in with letters, and most of the homework is with letters, but we really need that orientation sometimes. Okay, let me get the feedback. And do part C and then A in number 2. .30 seconds more. Alright, so the top one, we move, if it's a negative exponent, we move it to the other side of the fraction. The reason why we do that is, let me do this one out the long way for a moment. If I just focused on this part, we would do it like this. 1 over 4 to the second. Which is 1 over 1 over 1 over 16. And then you do copy, dot, flip. Copy the top one, dot, and then flip the bottom one. And then we get 16. But the faster way to do it is just take this and move it up. And then you get 4 to the second over 1, which is just 16. So a negative exponent means move it to the other side of the fraction and change the sign of the exponent to positive. All right, and so we're going to use that idea down here. We're going to move, now the 3 has its own exponent of 1, same as the 6. They don't move around. This one moves down, this one moves up, and this one also moves up. So what I'm going to get is the 3 stayed put, the a to the 4th moved up, b cubed was already there, and b squared moved up to join it. And the only thing on the bottom is this 6, and then this a to the negative 2 moved down, became a to the positive 2. And then 3 divided by 6, divide by 3, and then these a's, divide by a squared, divide out, it knocks out 2 of these, and then these are going to combine. So what I'm going to get is a squared, b, visualize 3 b's, 2 more b's, b to the 5th, over 2, and that's it. And give me a little feedback on part C and 2A. It's a little more complex now. In 2B, go ahead and do that. $30 more. All right, I'm going to do this more than one way because there's a lot of different approaches to this. One way to do it is put the unwritten exponents on these guys, those up to the first. Distribute this -2 power as long as it's all one term. There's no addition or subtraction signs in there. You can distribute that exponent to every one of these. And power to a power would multiply the powers. So it would become 2 to the -2 x, and then we'd multiply -3 and -2 to become +6. And on the bottom it becomes 4 to the -2 x, 2 times -2 is -4, y. 5 times negative 2 is negative 10. Now what I accomplished was I got rid of the parentheses. And now there's just one exponent in every number. What you can kind of think of like this x right here has two different exponents on it. It's being affected by the negative 3, and then it's being affected by this exponent. But now every component has just one exponent on it. And now I'm going to do my moving around stuff. If it has negative exponents, it moves around. Don't cancel. Don't try to reduce this until you turn them all to positive exponents. So then I'm going to have 4 to the second moved up to the top. So x to the 6th stayed there. But it's joined by x to the 4th that moved up. And it's joined by this y to the 10th that moved up. Now on the bottom, the 2 squared moved down. And nothing else is going to be there. So this is going to be 16. These two x's combine. Visualize 6 of them and 4 of them. Now there's 10 of them. And then 16 divided by 4 is 4. And that's my result. 4x to the 10th, y to the 10th. Give me a little feedback on 2b. Okay, Nadine, you were starting to get it, and then this one was complex enough that it confused you.
Yeah, I think it's because you have to distribute the powers.
Distribute. Okay. That reminds me, I was going to show another way. Thank you.
I agree with Jeremy, crazy math.
Okay. Now, here's another way that this could have been done. And there's lots of different ways you could have done this. But when you raise something to a negative power, what does it do? It flips over. Like for instance, let me jump up so there's extra space. If I had 2/5 to the negative 1 power, it would raise 2 to the negative 1 and 5 to the negative 1. And then the 2 would jump down and then the 5 would jump up. So what it does, what does a negative exponent wind up doing? Flipping the fraction over. Okay? So it just kind of flips things over. So we could take that negative on the outside and we could deal with that first. Now, if this causes you to be more confused, you don't have to follow this, but oftentimes seeing it from more than one point of view adds insights. So what I'm going to do is I'm just going to leave everything inside exactly the same. 4x squared y to the 5th, but I'm writing what was on the bottom up on the top, what was on the top down at the bottom, and then instead of to the negative 2, it's going to be to the positive 2. So what did the negative part of the exponent do on the outside? It flipped everything around. So that's one way to do it, another way. And then another thing we could do is we could move this thing up here at this point. You don't have to distribute this to everything. You could reduce what's inside the parentheses first if you want to. There's just so many different ways you could do this. All right. So then this becomes 4x squared x cubed y to the 5th over 2, all of that squared. And then I'm going to reduce the 4 over the 2 becomes 2x to the 5th, y to the 5th over 1 squared. And I'm still going to get exactly the same thing. Square the 2 and you get 4. Power to a power, we multiply x to the 10th. Power to power, multiply y to the 10th. In the end, I'm going to get exactly the same thing, but there are different ways you can approach this.
Yeah, that one I understand way better. Thank you.
You're welcome. All right, so number 3. Convert the following scientific notation numbers into standard notation. So these numbers are in scientific notation, meaning that the decimal is immediately to the right of the first non-zero digit. There were some of these problems in the homework. You had to read about it. and then it's times 10 to some power. So convert these to regular, standard. What are they as regular numbers? $30 seconds more. Okay, so this first one, we normally had the decimal point right here. But we're going to move it, every time you multiply by 10, it moves it to the right. 2.8 by 10 is 28, and so on. We're really multiplying it by 10 6 times. So we're going to move it to the right 6 places. 1, 2, 3, 4, 5, 6. And that's where the new decimal point is. And then we have to fill in zeros. And so the real answer is 2, 8, 0, 4 more zeros. Come back from the end and put my commas. 2,800,000. And the reason for scientific notation is if you take your calculator and let me show you real quick on my calculator. I'm going to put my camera on. And let me put this close-up of my calculator. Let me get the light on.
Yeah, here's a tip. There's also a camera function on Discord, so you can turn it on like that, and everyone can watch you that way.
Cool. So let me do this, and then I'll try that out. Okay. So if I take, let me clear all this. If I take a really big number times another really big number, there's not enough, my display won't hold the answer. And what does it have to do? It has to put it in scientific notation. So it counts the number of zeros, and that E12 really means 6 times 10 to the 12th power. And the same thing happens when you have numbers that are too small. Point and a whole bunch of zeros 5 times point a whole bunch of zeros 2 is going to give you an incredibly point, and there's only so many that it can display. So when we use really big and really small numbers, we have this. So yeah, let me close out this. So how could I have done this in Discord? Landon?
Okay, so you see right there, where you press the screen share button, there's another button that says video.
Yes. All right.
Yep.
Just turn on the camera, and then I pick which.
There you are.
So if I pick this one, I'm over here.
And it doesn't turn off your stream. It doesn't turn off. Yeah, so people can see both your face and your screen at the same time. It's very nice.
Oh, so now you're seeing both.
And they can also choose which one.
They can choose which one. Okay. So now I have a document camera, and I'm not seeing how to go to the document camera.
Okay, so right beneath where you're kind of seeing your face.
Yeah.
There's a camera button, right?
Yeah.
Excuse me. It's a drop-down menu, and I want you to select that camera through the drop-down menu right there. That should be the right one.
All right, and now.
Oh, a camera can't be used in two applications at once. So if another application is using your camera, which in this case is the camera app, you'll have to shut it off.
Shut the camera app off.
And then you're going to want to restart your camera on Discord, so just click it twice or something. And then go to the camera you want.
Got it. And then I go here, and then my camera. All right, it turns on the camera automatically when you do this in Discord. Cool. And now I just go over here, and it turns off the camera. And now I'm back to where we were at before. All right, awesome. Thank you. So I could have my face showing at the same time and going back and forth. I didn't realize that. All right, so let's go to this next one. So we just moved the decimal point 4 places to the left. 1, 2, 3, 4. And it's going to create 1, 2, 3 zeros. So this answer is 0.000392. Okay, and then convert the following standard notation numbers into scientific notation. So do 4A and B. Seconds more. So this first one, you move the decimal. The decimal was right here. Where the decimal has to go is right to here, to the right of the first non-zero digit. You always get a number between 1 and 10 in scientific notation. And then, so it's going to become 9.38. The rest of those zeros I don't need to write. Times 10. Now we just got to figure out what power. And there's 3, 6, 9, 10 places I would move. And I always guess a positive number, and then I check my work and say, does it make sense that if I move this to the right 10 places, I'd get this? Yes, so that's my answer. So I'm going to do the next one, similar. You have to move the decimal so that it's to the right of the first non-zero number. It's going to be right to here. So it's going to become 5.921 times 10 to the 9. Count how many places. If now this one I'd go individually. 1, 2, 3, 4. 1, 2, 5 places, and I start with a positive number and say, does that make sense? Oh, if I move this to the right 5 places, it's not going to be this. So it doesn't make sense as a positive, so it must have been negative. And then move it to the left 5 places, dividing by 10 5 times would create this. All right, give me a little feedback on numbers 3 and 4.
I have a question.
Yes.
That's really good.
It's just for my own knowledge, but why did we start with section 3 and then go back to
Oh,
1?
that's really good, dude. Shit. So it's
Say that again.
I wanted to know like why we started the class with doing chapter 3
Oh,
and then we're going back.
and then why we're going backwards and picking up some things and so on. All right, yeah, because look at the list. It's a good question. On the right-hand side of this screen is showing the order in which we're going to do everything in this book. And the main thing is functions, how to work with functions. That's chapter 3. And then we're going to be going in chapter 6, exponential and log functions. Those are the 2 main themes in this course. And then there's some miscellaneous things. For instance, exponents and scientific notation. There's only 2 sections in chapter 1 that we're going back to do. And then radical and rational. And then there's only 2 sections in chapter 2, a section here in chapter 4, a couple sections in chapter 5. And why this is the case, why we bounce around like this, is it's kind of the nature of textbooks now. Probably not too many of you have the physical copy of the textbook, but they make these textbooks gigantic. So, you know, you're never going to cover the whole thing in one course. And this is the same textbook if you go on the next class in the sequence to pre-calculus and trigonometry. That uses the same textbook. So there's no way we'd be covering, you know, significant portions of this textbook. We're only going to do the portions that we need. And if we, and there has been some, like, when we first set up, this college algebra, mainly we need to make sure they know about functions and how to do inverse functions and stuff, and mostly they need to know about exponential and log equations in chapter 6. But then it's like, oh, but then it'll be too long since they've had certain things. Like, you've probably had negative exponents and fractional exponents, but most students in this class need a refresher on that. So that's why, even though it's not a theme in this class, we pick it up and we say, let's just do these exponents and radicals. And what we tend to do as well is we tend to not put all the things like, although this could have been done first, 1.2 and 1.3, we're going to need them soon. So we tend to put them just before you're going to need them, so that it's nice and fresh when you do need it. And it makes it seem a little bit more cohesive from your end, is that it's not just randomly flipping around from topic to topic, as we're going to topics that are necessary to learn the next stuff. Does that answer your question?
Yes, thank you.
You're welcome. All right, so now we're going to go to number 5. Get the answer in more than one way. Consider expanding and then condensing as one of your methods. Remember we did that expanding and condensing? I'm going to show it to you real quick in case you don't remember that, when we had these from last time. A problem expanded out and then simplified, and then what was the rule? Okay, so do this problem. We're not so much interested in the answer as that you can get it in more than one way. And if you can get it in like 3 or 4 ways, do it. As many ways as you can in the time allotted. But definitely get it more than one way. Okay, 30 seconds more. All right, so one way I can do the expand out. And then divide this by 3, divide this by 3, divide this by x, divide this by x, divide that by x, divide this by x. And then these all get multiplied together. 1 times 1 times 1 is 1. And then we're left with 4x squared down at the bottom. Alright, let me show another way. I could reduce these right off the bat. But then the x squared over 4x to the 4th. Let me show you another way that could be done. This could be x to the, I'm going to leave the 4 down here. One of the rules that we learned last time, an exponent rule. Rules of exponent. When you're dividing, you take a minus b. X to the a divided by x to the b is subtract. So I could use this, but you got to do it really precisely. 2 minus 4. That 2 minus that 4. Oops. This is x to the negative 2 over 4. And that's the same answer as this. It just looks different. Now, the textbook often gives extra instructions. It says, write your answer with positive exponents. So if we were to write this answer with positive exponents, we would move that down to the bottom. And when everything is moved to the bottom, why is there still a 1? Because anything of itself times 1. So there's still a 1 up here. So we still see that it's the same answer, but it was a different way of going about it. Okay. We could have also done it yet another way. Cancel out the 1 and the 4, so we still have that. The 3 and the 12 to get the 4 on the bottom. And we had x to the 12th over x to the 4th. Let me show you another way. If you take it from the point of view of this, could be done this way. 4 minus 2. And then you just get a 1 left over up here. So this one would come down as a negative exponent and then subtract. But it's kind of like b minus a instead of a minus b, but it's left down in the bottom. This would also give us the same answer at the end. There's different ways you could go about this. All right, give me a little feedback. Does that add insight or nah? I already knew this in the main chat. So same instructions. Get it in more than one way. Part B. Okay, 30 seconds more. Alright, so one way is going to be, I'm going to take this negative 2 and get rid of the parentheses. I'm going to leave the top just the way it is for now. But I won't have this parentheses. And remember, there's really a 1 right here. Power to power you multiply. 1 times negative 2 is negative 2. A, negative 2 times negative 2 is 4. B, 4 times negative 2 is negative 8. Okay, so we could have gotten rid of the parentheses first. And then everything with a negative exponent is going to change signs. So then I'm going to get 2 squared up top and b cubed up top. And on the bottom there's going to be an a squared and an a to the 4th. And then this one moved up, so it's over here. And then this is 2 squared is 4. There's 11 b's up on the top, and there's 6 a's at the bottom. That's my final result, but that's just one way to do it. Another way could have been done is I could have moved all of this up here because I'm looking at that negative exponent, and I'm going to change it to a positive exponent. So this would be a to the negative 2, b to the 3, 2a to the negative 2, b to the 4th, in parentheses, all not negative 2 but positive 2 because it moved up. And then I'm going to have a to the minus 2, b to the 3rd, times 4a. I'm going to distribute this exponent. The negative 4, b to the 8th, all over 1. And then this is going to equal, and then now I have 4, a to the negative 2, a to the negative 6 makes a, negative 4 makes a to the negative 6, b to the 8 and 3 is 11 over 1, and then this is going to come down to the bottom, and I get 4b to the 11th over a to the 6th. Exactly the same answer as I had before, but a different approach. Okay, and I'm going to skip this one because we've spent long enough on this, and let me ask, are there questions? Homework questions, or any other questions anybody wants to ask?
Would you be able to do problem number 4 on page 29?
Page 29, number 4. Explain what a negative exponent does. All right. Good question. And let me ask if there's anybody that's got an idea that might work here. What does a negative exponent do? Go ahead and use your mic if you've got an idea might get us started. Yes.
What I put on mine is I don't like it was kind of hard for me too, but I just put that it turns into a fraction.
Ah, gotcha. Turns into a fraction. And there's many different points of view, but that's a nice point of view on this. Explain what a negative, it's turned something into a fraction. It doesn't make something negative. Does not equal negative 8. Is like this. It makes it, and another thing we might call it is instead of repeated multiplication, because that's what exponent, a positive exponent is, negative exponent is kind of like repeated division. This is dividing by 3 three times. And when you divide 1 by 3 ones, you get 1/2. Divide by 1 by 2 and you get 1/2. Divide 1/2 by 2, you get 1/4. Divide 1/4 by 2 and you get 1/8. And so it just, there's kind of a repeated division instead of repeated multiplication. 2 to the positive 3 is repeated multiplication. But this is repeated division. So a couple different points of view. And does that answer your question?
Yeah, thank you.
You're welcome. Any other questions? All right, we're going to take a break now. We will start again at 1:30 p.m. with radicals and rational exponents. And before I take my break, is there anybody who needs to talk to me individually? All right, I'll take my break. Number 14, we can come back to that. Alright, we'll get going again. And topic is section 1.3, radicals and rational exponents. And your first task is 2 trivial problems. Put a T or an F next to each one of these, true or false. And there should be enough time to realize that this one is true and this one is false, because 12 minus 4 is really 8. So in the same vein, put a T or an F next to this one. And then, alright, so this one, it turns out this is, well, how do you do these? Aren't these the same thing? No. The one on the right, you do this individually, that's 2. And you do this one individually, that's 3. And the one on the left, you have to do the addition first. And is the square root of 13 equal to 2 plus 3? No way. It would have to be square root of 25 to be 5. Square root of 13 is somewhere between 3 and 4, and this is 5, so this is false. Right. Go to the next one. Put a true or a false next to this. Alright, time's up. So the one on the right is easy to see. The square root of 4 is 2. The square root of 9 is 3. 2 times 3 is 6. The one on the left, you can't do it the same way. It doesn't mean square root of 4 times square root. It means the 4 times 9 has to happen first. 4 times 9 is 36. But when you take the square root of 36, you get 6. So these are equal, so this one is true. Let's go to the next one. Square root of 25 minus 9. True or false? Okay, so the right side is the easier one. 5 minus 3, and that's 2. On the left side, you have to do the subtraction first. That's 16. And the square root of 16 is 4. And 4 is not equal to 2. So this one is false. And then there's 2 more. We already did the F. Let me get rid of that. Do this one, and let me call it F. And the right side, that's the easier one. That's a 3, and the square root of 25 is 5. So this one is 3/5. But is the left one 3/5? Do you take them? Now you gotta think of what fraction times itself will give me 9/25, and that is 3/5. Because is 3/5 times 3/5. Multiply the tops, multiply the bottom. They are equal, so this one is true. Alright. And now, why did we spend all this time with this? Well, we want to generalize the rules. So, a generalized rule is the square root of a times b is equal to the square root of a times the square root of b. And I want you to complete the right-hand side for all of these rules. And I want you to do this inside of your group chat. And I'll give you a minute. Type it up, but don't hit enter yet. I'll tell you when to hit enter. Go ahead and hit enter. Discuss it in your group chat. Okay, group 5. What do you have for part B?
Um, Sorry, hold on. Daniel here.
Okay.
Um, we put the square root of a over b equals the square root of a over the square root of b.
All right. I go along with that. And what do you have for C?
I don't think we don't really get to that one, but I think I just put square root of a plus b does not equal square root of a plus square root of
Very
b.
good. You cross this out. And what about the bottom one?
Square root of a minus b does not equal square root of a minus square root of b.
From all the examples we saw earlier, if it was, another way to look at it is if it's one term inside the square root, then you can distribute the square root to all the individual parts. But if it's more than one term, remember terms are separated by addition, subtraction, or an equal sign. If there's more than one term inside, then if you try to distribute it, you get the wrong answer. This is very similar, because we've already studied inverse functions. It's very similar to this. Because square root is the inverse of squaring. And if it's one term here, you can go ahead and distribute it, and you'll get the right answer. But if it's here and you try to do it, it's not true. Why is it not true? Because you're missing, there's going to be, you'd have to do it, you'd get two middle terms. There'd be a plus 6x, plus a 3x from one of them and plus another 3x from the other one. So that's why if it's one term inside the parenthesis, you can distribute squares or square roots. If it's more than one term inside the radical or the parenthesis, then you cannot distribute it. you get wrong answers. All right, so the topic today, one of them is radicals, and having these rules down is essential. This is some of the most common mistakes. Just, breaking them up into separate square roots when there's more than one term inside. All right, so let's look at simplifying square root of 75. All right, and note, when you punch square root of 75 into your calculator, and you get something with all these digits, 8.66, so on, that's called approximating, not simplifying, because you're not getting the exact answer. The exact answer to square root of 75 is a decimal, goes on forever without a repeating pattern. It's an irrational number. And so you'd have to chop it off at some spot. And you might think, well, this is accurate enough. Well, it depends on your application. It might not be nearly accurate enough if you're doing some application like you're sending a rocket ship to Mars or something. You might need a hell of a lot more accuracy than this. All right, so how not to simplify? Square root of 75, well, think of 75 as 25 plus 25 plus 25. And then break them up into separate square roots. But if we did that, we'd be using C, which is not true. This doesn't check because it turns out that 15 that we claim was the answer, if you take 15 times 15, you get 225, not 75. So it's clearly not the correct answer. All right. This word fails to work because of property C above. All right. So how do we do this? We are going to break up 75 into two things that multiply together. And one of those things comes from this list of perfect squares. When you square something, now one squared I'm leaving off because it's just one. Imagine this list going on forever. 2 squared is 4, 3 squared is 9, 16, 25, so on. These numbers are what we call perfect squares because they're a whole number squared. What we want is to break up 75 into two things that multiply together. I'm going to do it 3 times 25, where one of those things is a perfect square. And I like to put the perfect square second. And then I'm going to use property A up here. If it's all one term, I can distribute the square roots. Make two separate square roots, and this will be fine. Well, actually, I think it would have been better if I'd have put the perfect square first, because then I wouldn't have to turn it around. And then I'm going to get 5, we tend to put the square roots in the back. 5 squared root of 3. So this, although this 8.666 isn't wrong, it's not doing what we're doing. We're not getting an approximate answer. We're still getting the exact answer. We're getting it simplified, though. Now, a lot of students at this point, and I would be one of these if I was first learning this, I would say, hell, this looks simpler, square root of 75, than this does, 5 square root of 3. I'd rather deal with this than deal with this. Why do you call this simpler than this? Well, because let's do this problem next. So, let me give you a moment on this one. Square root of 75 plus square root of 3. Go ahead and work it out. And when you get your answer, put your answer into your group chat. Okay, if you haven't already hit enter into your group chat, do that now. Discuss it. I'll give you a little bit more time. All right, group 2. What did you get for this?
We got a 6. Oh, we got a couple different answers. I'm just going to say mine. 6 square root 3.
Okay, and what else?
5 squared of 3 plus squared of 3. And a couple people just found it confusing still.
Okay, thanks for letting me know what everybody got.
Sure.
That's very helpful. All right, so the square root of 75, we're going to break it down the same way. I'm going to put the perfect square first this time. And then that's 5 square root of 3 plus, and I'm going to put the number that's out in front of this. It's not a 0, because 0 times anything is 0, but 1 times anything is itself. So there's really a 1. And then I'm going to make an analogy here. If I had 5y plus 1y, you all agree I would get 6y. Same thing with square root of 3's. 5 square root of 3 means square root of 3 plus square root of 3 5 times. And then there's one more. There are 6 of these. And this can be handled like this. And then these are the coefficients. We just add those. So 6 square root of 3. This would be great, but notice we can get all the way to here. And this is simpler. And that's why we prefer all the perfect squares to be taken out. Because when you're working with square roots, you often have other things that could be combined with it, but you won't be able to tell until you simplify something like square root of 5 down to 5 square root of 3. Alright. So when we do lots of computations with them, it works out much simpler too, if you just get the smallest possible thing left over inside the square root. Alright. So let me have you do square root of 20. And when you get your answer, put it into your group chat. But don't hit enter quite yet. Give everybody some time to process it. Go ahead and hit enter. Okay, group 1. Could you tell me how you did this as well as the answer you got?
This is Valerie. We did 2 times the square root of 5.
You got 2 times the square root of 5? Okay. And how might I get there from square root of 20?
It would be square root of 4 times the square root of 5, and the 4 is
Great.
the 4 is the square root.
Great. And so we took a number from this list of perfect squares and had it as one of the factors of 20. And then the other one stays inside the radical sign, but the other one comes out. All right. Now I'm going to throw you a curveball here. See what you can do with the cube root of 16. And I haven't shown you how to do cube roots, but make your best guess. When you get your answer, put it into your group chat. Go ahead and hit enter. Discuss it briefly. All right, group 6. Any ideas? Might get us started on this. Okay, group 6. Anais, are you there?
Yeah.
You got anything?
Someone in the group said 2 times the square root of 3 times the square root of 2.
Okay. That is at least something we have something to start with. That maybe we can get this. All right. Now, one thing, since this is totally new to us, that I want to point out here, is that if you don't write a number out here, then it's assumed to be a 2. This is a square root and a square root. And so, if it's cube roots to start with, the end result is also going to contain cube roots. Alright, so, important point, so I'm glad of this answer here to show is that this can't change into square roots. It'll still have cube roots. And let me start this out with an easier problem. Cube root of, let's say, 8. We're asking what number times itself 3 times is 8, and that's 2. Kind of like this, cube root of 100. No, 1000. What number times itself 3 times gives you 1000? That would be 10. Like this. Now, when we have cube root of something, we want the number that times itself 3 times is 16, but we're going to have to look at not a list of perfect squares, but perfect cubes to kind of estimate what this answer is. Now 1 cubed I'm going to leave off because it stays 1. 2 cubed is 8. 3 cubed is 3 times 3 is 9 times 3 is 27. 4 cubed, 4 times 4 is 16 times another 4 is 64. Now we can see that the cube root of 16 lies somewhere in between these two, because it's going to be bigger than 2 but smaller than 3 is our answer, because 16 is between 8 and 27. All right? But we're not trying to approximate it. We want to get, like we did with the others with the square root, we want to pull out. This time you can't pull out perfect squares. You have to pull out perfect cubes. Why perfect cubes? Because only like this, the reason why cube root of 8 is 2 is because 8 is in this list. It's something to the third power. And third root, third power, give you this. This is really the cube root of 10 cubed. 10 cube root, 10 cubed, kill each other off. These are inverse functions, you're back to 10. So here we want two things that multiply together to be 16, but one of them is not a perfect square anymore, but a perfect cube. Something from this list. Now, 16 can be written as 8 times 2. And then the cube root of 8 is 2. 2 times the cube root of 2. Now look at the answer that we proposed. It's really interesting. It's really close. In fact, this might have been almost meant to be this, but like notational wise, it's hard to write cube root inside of Discord in the chat channel or something like this. So maybe this was even what was kind of meant to be this over here. All right. Give me a little feedback on this. Did I were you okay up until this point and now the perfect cubes have knocked you off your loop? Or are you still understanding everything here? Give me a quick little bit of feedback. Because I can do another one with cube roots if people are confused here. Okay, looks like people are getting it. That's good. So let's keep going on. So the instructions here are to simplify all these things. So 8 to the negative 2/3. Can we give you a minute? Just a little bit more time, and then I'm going to work this out. Alright, so what I want to do is I want to show you, we started today with this practice quiz, fractional powers, and the bottom number came out as the root, the top number is the exponent. This is that same idea, but it's got an extra complication of a negative exponent. So what I like to do is handle the negative exponent first. Just bring it all down. And then do it like we had done it in the practice quiz. The bottom number comes out. Cube root of 8. Now the top number is the power on the 8. But you can delay it. Why would I want to delay it? Because I can do these with smaller numbers easier than with bigger numbers. Now, the idea is you can switch them around, do them in either order. I'm going to get 1 over the cube root of 8 is 2. So I'm going to get 1/4 on this. Okay. So then the next thing is, and it's supposed to be down here. Okay. We're going to be moving back and forth from radical form, which looks like A when there's a root sign. And then there's fractional exponents. And that's exactly what we were doing over here. We had a fractional exponent and we changed it to a radical format. So we can go in either direction. So do A, change it to the other format. If it's in a radical form, change it to fractional or vice versa. And then get it to be as simple as you can. And then put your answer into your group chat. And go ahead and hit enter. And group 2, what do you have for this?
X to the 12th third power. That's what we got.
Okay, so we just do the reverse what we were doing before. This 3 comes in underneath. And then we can reduce, because 12 divided by 3 is 4. And so the answer is x to the 4th. Now, writing a problem like this, cube root of x to the 12th, is kind of like asking, all right, what is something that when I multiply it by itself 3 times, I get x to the 12th? And if you think about it hard enough, you can kind of figure out, oh yeah, it's going to be x to the 4th, because x to the 4th times x to the 4th times x to the 4th, visualize there's 12 x's, and so on. But isn't it easier to just change it to its fractional format? And then, now, not always does it make it easier and simpler when you change it from one format to the other, but sometimes it does. How come this one became easier? Because you can easily do 12 divided by 3, and it becomes 4. And then that's, I mean, why work with it in this format over here when you could be working with it in that format? It's much, much simpler and easier to work with. All right, so convert, continue doing this, and do it with these next 2 problems. Convert them. If they're in one format, change it to the other, and then figure out what the answer is, and back and forth. So, let me give it a minute for B and C. Okay, if you're still on B, jump to C. I'm going to give you 30 seconds more. Alright, let's look at B. When I first look at a problem like B, I can't tell what the answer is. I need to do this to be able to, and I delay the making it bigger. I do the smaller first and then the bigger. And then that's 2 cubed, and then that's 8. So for me, radical on this problem is easier to process and figure out. As a fractional power, I can't tell what 4 to the 3/2 is. So I just change it to the other form and then voila. That doesn't always work, but in some problems like this one it does, and it just gives me a whole number 8. So there are times changing to the other format is very useful. This one, what's the fourth root of something squared? Well, if it was something to the fourth, then the fourth power and the fourth root would cancel each other out. But I'm going to change it to the other form. 4 goes underneath the 2. Now, 2/4, I can reduce that fraction. The same as 1/2. And now 9 to the 1/2, I can't tell what that is, except if I move this out. And then that's 3. This problem wasn't very convenient in a radical form. So I changed it to a fraction so I could reduce the fraction. But then I needed to change it back to a radical again so I could get it as a whole number. So this has going back and forth a couple times here in the same problem, really, to get this as simple as I could get it. So the whole idea that we're working on now is changing back and forth freely between these two formats. All right, do part D. So the bottom number comes out. It's the square root of 100 to the 5th. But square root of 100 is 10. And that gives me 1 with 5 zeros. So that's my answer. All right. Any questions? All right, so the homework is 1.3. When you get into 1.3 in the module, it will tell you two things. There's textbook problems it'll tell you to do, and there'll also be a worksheet, because the problems in the textbook aren't good enough. The worksheet, you're going to be doing that as well, and when you're uploading two different things, if you've got a scanning app, it'll concatenate it all into one big document. That's the best way to upload that. And we have a few minutes left. And if there's no more questions, I want to take us to a practice quiz problem that we didn't have time for. Let's go up to here. So, tuition at Boston College in 1980 was $48 per credit. In 2020, the tuition is $652 per credit. On average, how fast is tuition increasing at Boston College? So, we're back to practice quiz mode. Let me give you a minute to work on this, and then I'll put up the answer. in 30 seconds more. All right, when it asks how fast is something increasing or decreasing, it's really asking for the slope. And this part on average means that we're going to take it to be a straight line, and straight lines have slope. Okay. Now, slope, if you were visualizing this, you might think of it like this. Here's 1980, so this is the year, and here's 2000, and here is, you know, like $48 per credit hour, and here's $652 per credit hour. Now this 48 would probably be much lower. And technically speaking, we wouldn't want to make a graph like this. We'd want to go like 100, 200 equal mark units. But I'm just going to go really quick here with this graph and say that it's from this point to this point. Now, it might have been that tuition was steady, and then only very recently it went up really fast. Or it might have been most of it went up here, and then, but it doesn't matter. When we're finding on average, we're finding the slope of this straight line segment between these two. And this point is x and y coordinates, 1980, 48, this one 2000, 652. Okay. And then the slope, m, same as the rate of change, or how fast it's increasing, is change in the y over the change in the x. 652 minus 48 over 2000 minus 1980. And this is going to be 604 over 20. Now, what is this really saying? That it went up $604 in 20 years. And if I just punch this out in my calculator, I'm going to get $30.20 per year. That it, on average, if it had gone up $30.20 per credit hour each year, then it would have gone from there to that. Give me a little feedback on this. Were you able to get this on your own? Does it end the insight? Does it?
Yeah.
Yes.
I got like half of that, but I think I see you put like 2000, but it was actually 2020, so I think it would have been like
Oh,
40 years.
thank you. I screwed up. This is 2020. Thank you very much. I really need that when I screw up. And so this is 40. So you're going to get half of this, $15.10 per year is what it is. Okay, so a little feedback there, and we will stop here and you all have a great weekend.